Okay, in the topic subsystem design, we are going to study about our subsystem counter. As you have seen in IC designing at subsystem level has to follow data path and hierarchy, and hierarchy goes to top-down design methodology and satisfying the three entities: less area, low power, and high speed. We have come across so many subsystems, combinational circuits and sequential circuits. In this class, we are to go for designing of your counters. So first we'll start with counters. We'll define a counter. So what is a counter? Counters are sequential circuits which count through a specific state sequence. So you can design to count through a specific state sequence, and that is with respect to a clock. So for each clock pulse, we can change the state of your flip-flops, and over a set of clock pulses, we can make it count through a specific state sequence. What is specific state sequence? You can make it to act as a up counter, down counter, or you can also count through other fixed sequences. So you can make it to act as a up counter for a certain duration, then down counter for a certain duration. So counters are sequential circuits which count through a specific state sequence. They can count up, count down, or count through other fixed sequences. So we are having two different types of counters. Ripple counters are asynchronous counters or synchronous counters. So in ripple counter, clock is connected to the flip-flop clock input on the LSB bit, and for all other flip-flops, flip-flop output of one will act as clock to the next one. So this is not synchronous, it is asynchronous. So output of one flip-flop will act as clock to the next stage. So output is delayed more for each bit. So, and for if you go for synchronous counters, the clock applied is same. So what do you mean by clock? Clock is nothing but a sequence of pulses, high and low, with duty cycle 50%. So what is 50%? The on time is equal to off time. So it is a set of sequence of square pulses where on time is equal to off time, which is having 50% duty cycle. So that clock, if it is applied to all the flip-flops simultaneously, then it is called synchronous. And you can design the logic to make it as to count as a specific state sequence. You can count from 0 to 1, 0, 1, 2, 3, 4, 5, 6, 7. That is up counter. 7, you can start with initial value as 7, 7, 6, 5, 4, 3, 2, 1, 0 down counter, or any state sequence. Okay, that state sequence is under your control. So next here, asynchronous counter or ripple counter. So in the right side diagram, we are showing one flip-flop where clock is the input and it is positive edge. So you can see the triangle symbol, that is a positive edge. And here we are designing a T flip-flop, and that is using a D flip-flop where what is D flip-flop? Data flip-flop. T flip-flop means toggle flip-flop. For toggle flip-flop, for every clock pulse, output will be complement of the input. So how to generate complement? Output value must be given to a NOT gate and that must be given to the input. But instead of giving to a NOT gate, you know, for a flip-flop, you get two complementary outputs, Q and Q bar. So that Q bar is fed as input to the flip-flop. So if you see the first flip-flop where output is A, we are connecting that black color dot output A bar as input to D. So for every clock pulse, the complemented value will be given as the input, and this output is acting as clock to the next flip-flop whose output is shown as B. Okay, so if you see the same output is fed as clock to the next stage. Okay, so if you see the point, the clock input for the flip-flop B is nothing but complemented output of flip-flop A. So output for A flip-flop is capital A, but we are connecting A bar as clock to the next stage. And all these pin flip-flops can be reset to the initial stage by the reset button. So once you click reset as 1, so this terminologies, you can go for an active high or active low. So if you don't keep a bubble, it is active high. So active high to the reset will make it come to the initial stage. So first CP tells it is a clock. It is a set of on and off pulses. So this square pulses on and off with duty cycle 50%. On time is equal to off time. Together they form a clock. So it has a transition from 0 to 1 and 1 to 0. So whenever there is a 0 to 1 transition to the clock, your output D, okay, output D so look into the waveforms. Whenever CP bit was 0 to 1 transition, at that time clock transition was occurring. At that time input is fed to the output. Okay, input is fed to the output. What is the input? Already A was 0 initially, means A bar is 1. So that 1 is fed as input to the D bit. Okay, so once you apply a clock, the 1 is fed as output. So there is a transition from 0 to 1. If you see, there is a transition from 0 to 1. So this will remain as long as there is a next clock transition. So next clock transition is 0 to 1. So when there is again a clock transition 0 to 1, when again there is a clock transition from 0 to 1, the output will change from 1 to 0 because already A is 1, means A bar is 0. This 0 is fed as again input to the, this 0 is fed as again input to the first flip-flop. And whenever there is again clock transition, this 0 is fed to the output because it is a normal D flip-flop implementing as T flip-flop. Okay, so output for every clock pulse, output will do toggle of the input values. So the toggling, how we are achieving by applying A bar as input to the D. So you can consider it as a D flip-flop only. The only thing is the input fed to it is a complementary value of the output. So like that for every clock pulse, your complemented value is fed. So the 0 becomes 1, 1 becomes 0. So like that, you are going to get output A as 1010 transitions with slight delay. So the delay you can analyze with respect to CP. Now this A has its A bar. Okay. It has A bar, which is reverse of this A, complemented value of this A. Because that complemented value of A is acting as clock to the next flip-flop. Okay. So here also B is the normal form. B bar is fed as the input. So if you analyze as a D flip-flop, for every clock pulse, D input is fed to the output. And as a T flip-flop, we are complementing the, we are going to toggle the output. Okay, so for getting the toggle operation, we have given output complement value as the input. Okay, now if you see, here A is having 0 to 1 transition, then A bar is 1 to 0 transition. So that is not counted. If you see the arrow mark pointed where A is 1 to 0 transition, then A bar becomes 0 to 1 transition. So where A is 1 to 0 transition, there A bar will be 0 to 1. So for that 0 to 1 transition, your B value will change from 0 to 1. And again, where A is 1 to 0 transition, there A bar is 0 to 1 transition. At that time, again, B value will change from its present value. Present value is 1, so next value becomes 0. So like this, you are going to achieve ripple counter or asynchronous counter where clock is not synchronous to all the flip-flops. So you can make it to add, this is the only 2-bit flip-flops. If you add 3 bits, it will count from 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now, if you add one more bit, additional bit to D, it becomes, okay, it becomes a 4-bit asynchronous or ripple counter where you can get transition from all zeros to all ones. So for a 2-bit, it is changing transition as 0, 0, 0, 1, 1, 0, 1, 1. Again, it will reset to 0, 0, 0, 1. And in the diagram, you can see the blue color lines are telling the state transitions. So first CP 0 to 1 transition is changing A value, but for changing B value, you require complement of A. So A is 1, 0 means B is 0, 1. Sorry, A is 1, 0 transition means A bar is 0, 1 transition. So whenever A bar becomes 0 to 1 transition, second flip-flop B output will make transition from its present state. So here A is 1 to 0 means A bar is 0 to 1. At that time, B is changing. So these circuits are called ripple counters because each edge sensitive transition, positive in the example, causes a change in the next flip-flop state. And the changes ripple upwards through the chain of flip-flops. Each transition occurs after a clock to output delay from the stage before. So here we want to represent the delay produced in a ripple counter. So it is initialized. We have considered a 3-bit counter where 3 flip-flops, initial values C equal to B equal to 1 is all are 1. In decimal value, it is 7. And for next clock increments, the count value must become 0. Okay. So here it is an up counter 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. So the decimal value is 111. So for the next clock, it has to be reset to initially all zeros. So here we are going to see the state transitions occurring at the outputs of flip-flops ABC. So for every clock pulse, the clock to output delay TPHL causes an increasing delay from clock edge for each stage transition, and thus the count ripples from least to most significant bit. So here least significant bit is A, most significant bit is C. So there are 3 flip-flops, outputs are C, B, A, and because of this count to clock to output delay TPHL, it is propagating from least significant bit to most significant bit. This delay throughout the flip-flops produces an n bit delay. Okay, so for n bits, it is n into TPHL. So here we want to eliminate the effect of ripples. So we are using a common clock for each flip-flop, and we want to generate a combination circuit to generate the next state. So for an up counter, you can use an incrementer, which is generating the next state. So the right side diagram is representing the D flip-flops, 4 D flip-flops, D3, D2, D1, D0, and corresponding outputs Q3, Q2, Q1, Q0. And each time this inputs will vary, and because clock is common, it will count from 000 to 001 to 010, 011, 100, 101, 110, 111. So this increment values will be fed to the D. For every clock, D is returned to Q. So we have to design this incrementer such that the hardware logic is incrementing the values and giving it to the D inputs. So here the incrementer logic is analyzed with a XOR gate and AND gate combination, and this AND gate is nothing but carry output. So we have a enable pin. Once you enable it, initially output is 0000, and those are fed as an input, and your enable bit is 1. So 1 into 0 is 0. Okay. So but 1 into 0 XOR operation becomes 1. So initially Q3, Q2, Q1, Q0. Initially Q3, Q2, Q1 is 0 were all zeros. Now it becomes 0001. And for one more logic, it becomes 0010, 0011, 0100, so on, all ones. So that was done with the help of this incrementer logic. So we have to design an incrementer logic such that the internal logic XOR bit complements each bit, and AND chain is causing complement of bit if all bits toward LSB from it are equal to 1. And we are also using a count enable, forcing all outputs of AND gate to become 0 to hold the state. And there is a carry out bit added as part of the incrementer, and this counter will enable to count act as a 4-bit counter. So left side there is an incrementer logic. You can apply the values. Each value it is fed to an XOR gate, and that output is fed to D. Whenever there is a clock pulse transition, the inputs are written into the flip-flop, and it changes the value of Q. Okay. So what is flip-flop? It is a edge triggered flip-flop. So for every edge trigger, Q equal to D. So earlier we have seen one incremental logic for synchronous counter using a carry chain logic, where the symbolical representation is Q3, Q2, Q1, Q0 are the outputs. There is an enable pin and a clock at the input side, and there is a C out bit. And here the carry chain is analyzed with a series of AND gates through which the carry ripples, and this is yielding long pass delays, and this method is called serial gating. We want to replace the AND carry chain with all AND gates in parallel. So if you see the previous diagram, this AND gate was producing the carry to ripple through all these gates. So the series of AND gates through which the carry ripples is yielding long path delays in this previous diagram. So this was replaced with an AND gate in parallel. So this method of designing the AND gates to generate Cout is called series gating. But whereas this method of designing each stage corresponding Q value and C1 is called parallel gating. It is like carry look ahead adder and it reduces path delays. And this symbol is for synchronous counter. And what are the other counters you can analyze is down counter, where count is decremented from a initial value. So instead of upward, here you are going to count downward. So, and you can also go for an up down counter where count up or count down depending on value of the control input, such as up or down. And parallel load counter where it has a parallel load of values available depending on the control input. And you can go for a modulo counter. So modulo counter is like divide by n. So counter is designed such that it is counting up to a specific value. Count is the remainder of division by n, or it is a power of 2. And you can make it an arbitrary number of states. For a BCD counter, it will count up to 0 to 9. It is called modulo 10 or BCD counter. So here we are also showing one counter with a parallel load where along with enable pin, we have a load operation. So this load operation is going to make it as act as when load is 0, it is when count value is 0. Okay. So to the left side, there are two bits. One is count and one is load. When count is 0, it will hold the stored value. So all Q3, Q2, Q1, Q0, it will hold the same value. But once count bit is 1, it is going to count as up counter. So 000 becomes 001, 001 becomes 010. Like that, it becomes all ones for a 3-bit counter. For a 4-bit counter, it is all zeros to all ones. So that depends on the count bit. Count bit is 0, it holds the value. Count bit is 1, it is going to act as an up counter. Now, if load bit is 1, what is happening? You can load your data D values onto the D3, D2, D1, D0. So from that value, you can make it as act as an up counter. So that is created with this logic. So synchronous BCD counter. So BCD itself, it is telling it is can count up to modulo 10, that is 0 to 9. Okay, so the combinations from 1010 to all ones are not considered. They don't cares. So you can see current state in 8421 format. It is Q8, Q4, Q2, Q1, which is all zeros, 001, 0010, so on 1001. So if it is acting as a synchronous counter, for every clock pulse, 000 becomes 0001. For the next clock pulse, 0001 becomes 0010. For the next clock pulse, 0010 becomes 0011. For the next clock pulse, 0011 becomes 0100. So it is counting 1 bit. So finally, for 81000, it is 1001. Then for the next clock pulse, 1001 becomes reset to its initial value. Okay. So how we have to analyze is for each next state values, you have to see when the output is 1. So you have to generate SOPs based upon the K map. So you have to take those combinations for which output is 1. You can map on a K map. You can use the don't cares, then go for 2 cell, 4 cell, 8 cell groupings. then generate the equations like this, which are optimized, two-level optimized next state equations for D1, D2, D4, D8. So based upon that, you can create the hardware related to this one. For D1, D1 input, this is the hardware. For D2 input, it is this one. So this combination of output values are taken and given to corresponding AND and OR gates, and that is fed as input to the D values. So here, if we are not considering don't cares, what happens is for a 4-bit, the next states are written as 1010, next state is 1011, and 1011 next state is 0110. So like that, all the next states are written, and they are represented in a state diagram. For the BCD counter design, if an invalid state is entered, return to the valid state with 2 clock pulses. For an n-bit binary counter, whether it is synchronous or asynchronous, you can use a clear pin and load pin. Okay, so everywhere you have to write the current state and present state based upon the modulo values. It is an asynchronous 4-bit binary counter with an asynchronous clear pin. So this clear pin, what it does is asynchronous clear pin to make it as act as a modulo 7. So once it is modulo 7, means it is up to counting from 0 to 6. This clear pin will make it to this clear pin will make it to come to initial state. So it counts from 0, 1, 2, 3, 4, 5, 6. Once it is all 7s, sorry, it is 7. It is all, it is 7 means Q2, Q1, Q0 are all ones. Those ones are given to an NAND gate. NAND gate output is 0, and this 0 is fed as input to the clear pin. Clear pin is a active low signal, so that 0 becomes 1. And once it is 1, all the outputs Q2, Q1, Q0 becomes initialized to 0. So this type of modulo 7 counter will detect counting from 0 to 6, 0 to 7. Okay, once 7th bit once comes, it becomes again 0. So 0 to 6 only it will count. Once 7th bit comes, it will detect it as 0, 0, 0. So the same logic is applied for a synchronous load. Here we are using a synchronous load count of 6. So a synchronous 4-bit binary counter with synchronous load pin and asynchronous clear pin is used to make it as a modulo 7 counter. So the load feature to detect count 6 and load in 0. Here the count value is counting from 0 to 6. Then again it is 0. So using don't cares for states above 6, detection of 6 can be done with load Q4 and Q2. So here what we have done is in D3, D2, D1, D0, we have written all the inputs of this 4 D flip-flops as 0, 0, 0, 0. The moment it counts from 0 to 6. Okay, once it counts 6, 6 means Q2, Q1, Q0 is 1, 1, 0. So that 1, 1 is given to an AND gate. That AND gate output is given to a load. So once it is a load pin, just Q3 becomes D3, Q2 becomes D2, Q1 becomes D1, Q0 becomes D0. So all are initialized to zeros. Okay, so that's why it is a synchronous load and asynchronous clear pin. So what is asynchronous? So this reset, if you apply to active low signal, that is going to clear. But here our count value is controlled by load pin. So similarly, you can go on adding preset pin, clear pin, load pin to your design. So here what we are doing is we want to use a load pin, which is a actually we are designing it as a modulo 6 counter. So we are doing the load operation. So D3, D2, D1, D0 are fed with 1001. Synchronously preset 9 on reset and load 9 on terminal count 14. Okay. So it is 1001 means 9. We want to load that data, and for which we are using modulo 6. So we are using modulo 6 as the design. So once it is 6, 0, 1, 1, 0, you are going to generate an output 0, which is fed to your OR gate, and that is acting as a load. So asynchronous 4-bit binary counter with a synchronous load. Asynchronous 4-bit binary counter, asynchronous 4-bit binary counter with a synchronous load pin. So in the exam, you don't need to add all this reset clear pin. You can just go on designing an asynchronous counter as a ripple counter like this, 2-bit, 3-bit or 4-bit, or you can go for designing a synchronous counter based upon your state table, where taking the current state and the next state, you can generate corresponding input bits, and those input bit values, when they become 1, that combinations you can generate a K-map, and you can generate the hardware like this. So the hardware for D1 is directly Q1. For D2, it is a combination of Q2 plus Q1, Q0. So there is an AND gate plus OR gate given inputs as outputs of the flip-flops. So next state is generating the present state. Okay. So like that, it will count from all zeros to all ones if you act as a mods. Uh, uh, it is a 4-bit counter. It is a mod 16 counter, 0 to 15 it will count. If you make it as a mod 10 counter, it will count from 0 to 9. So next we'll discuss some more topics related to counters. So already you have seen counter is a sequential circuit which counts number of clock pulses. So the topics to be dealt are, already we have seen synchronous and asynchronous counter. So its characteristics, ripple up counter, ripple down counter, and how it acts as a frequency division circuit. So count by definition, one input clock, outputs following a definite sequence, count up or down counter, increment counter, decrement counter, controlling the sequence of events or states, are acting as a divide frequency, or it can be used for memories. So here, coming to counters, first you have to decide the number of bits. This number of bits will decide the number of flip-flops to be used, and will also decide the count value. So if you select number of bits as 4, it will count from 00000 to all ones in binary form. If you take it as a count bit as 8, it will count from up to 2 power of 8. So modulus of count number of states. Modulus of counter number of states. So you can go for a decade counter counting from 0 to 9, or you can go for a 4-bit counter counting from 00000 to all ones. So analyze up counters, down counters. Both can be synchronous and asynchronous. So this is a ripple counter. This 4-bit counter has 16 states because there are 4 flip-flops. Here we are using a JK flip-flop, and this JK flip-flop, all inputs are connected to 1, and all clear and preset pins are connected to 1. What it means is, in this diagram, so you can see we have made preset and clear pin inactive by giving it to a 1. As bubbles are connected, then this 1 becomes 0. So they are inactive, and all JK flip-flops are in the toggle mode. So how you make it act as a toggle mode? When both the inputs are 1, your output is complement of its present value. Q becomes Q bar. When both inputs are 1 for a JK flip-flop, Q becomes Q bar. And here, this 4-bit counter has 16 states, counting from all zeros through all ones. Then again, it will go to reset to 0. So it is called a modulo 16 counter. So whenever there is a, if you see the clock applied, will be having a bubble in your diagram. For each flip flop, if you see to the clock input, we have kept a bubble. Bubble indicates it is a negative edge trigger. Okay, whenever there is a transition from 1 to 0, this first flip flop will generate the will change the value Q from 0 to 1, and this will act as clock to the next flip flop. So there is a 1 to 0 transition in the clock. Your transitions of all the 4 flip-flop outputs will vary, and this ripple counter is going to count from all zeros to all ones. So here if you see, flip-flops triggered on high to low pulses. So clock toggles. Oh, okay. So if you see, so in the same diagram, both JK inputs are 1. Both JK inputs are 1. Q becomes Q bar. And so for a clock input, whenever there is a high to low transition, your first so each output of flip-flop, you can see whenever there is a high to low transition, the output is varying from 0 to 1. And whenever this is from high to low, output is varying from 0 to 1, each flip-flop output. Whenever the third row is going from high to low, again there is a transition from 0 to 1. So if you study in the reverse order, it is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Like that, finally it is all ones. So you have to read the Q3, Q2, Q1, Q0 in a reverse order. So this is a ripple counter, and we want to make it as a decade counter. So for that, we are connecting the logic is we have connected two outputs like we have shown in the earlier part. Decade means it is 0. It is a 4-bit counter. No, it will count up to 1001. So 1001. So 1007. Both the ones must be given to AND gate, and that output is fed as connected to the clear pin, where it will make our flip-flop outputs to come to initial state. So this is active low pin. Here also output generated is 0. So 0 is acting applied to all the clear pins. So the 0 makes it 1. So for that 1, output becomes all zeros. So count is at 1001. For the next clock pulse, okay. So you are going to make the counter reset to all zeros. So this is regarding decade counter, and this is a down counter where the flip-flop is all flip-flops are initialized to 1111, and for every clock they will do down counting, changing the ripple counting from all ones to all zeros. So here this is Q, Q2, Q1, Q0, and again it is an asynchronous counter. So how that is done is output of first flip-flop is fed as clock to the next one. So based upon this transitions, we are going to see a down counter. So this you have to for a up counter, normal output of each flip-flop is acting as clock to the next counter. Complement form of your output will act as a clock to the next state. So here counter used for frequency division. So in each state, this ripple counter was designed with a 4-bit flip-flop where output, if you see in this diagram, it is an up counter. Okay. So if you see output Q is acting as clock to the next stage, and this is bubble means it is a negative edge triggered. Without bubble, both JK inputs are 1 means whenever clock pulse comes high to low, your output changes to toggles its previous value. If 0 is there, it becomes 1. 1 is there, it becomes 0. And if you see the uh, clock pulse applied is initially clock pulse applied is 800 hertz, but as a clock is propagating from one stage to another stage, so the final LSB flip-flop clock pulse is, because you know from you have seen each of the negative edge is generating. So here if you see each of the negative transitions high to low was generating one more clock pulse whose time period was this is a high frequency, then the frequency is reduced, so time period is increasing, the on time off time period is increasing, the next 2s output time period is more, next 2s 4s output is again more. So as time period is increasing, corresponding frequency is reducing. So first flip-flop output is reduced by 4 by 2, it is 400 hertz. So the clock applied to the first flip-flop is having frequency 800 hertz. Okay, F is equal to 1 by T. So the time period of both T on plus T off is nothing but 1 by 800 hertz. So now the output generated of first flip-flop is nothing but clock to the next stage. So that is reduced by 2 times, it is 400 hertz. And in the next case, next flip-flop output is divided by 4, it is 200 hertz. And the third flip-flop output is divided by 8, it is 100 hertz. And the fourth flip-flop output is divided by 16, it is 50 hertz. So like this, uh, we have designed in synchronous and asynchronous counters where we can see that the it counts the number of clock pulses with respect to clock applied, whether it is asynchronous or synchronous. So once again, we'll go through the comparison of both the counters. So as we discussed, for ripple or asynchronous counters, flip-flop of one output, QA is fed as clock to the next stage. If there is a bubble, it is a negative edge triggered. Without bubble, it is a positive edge triggered. And if clock is same for all the flip-flops, it is synchronous counter. So as discussed earlier, asynchronous ripple counters, clock is not same. They're not clocked simultaneously. Circuit is simple. Speed is slow as clock is propagated through number of stages. Whereas for synchronous, there is no connection between output of first to the clock of next flip-flop. Flip-flops are clocked simultaneously. Circuit becomes complicated and speed is high. And the synchronous counters can be analyzed in terms of three ways: up counter, down counter, up down counter. Counters anyway, not only synchronous, asynchronous, synchronous, both we can make it to design as three methods. This was regarding the subsystem design counters. So you have to take 3-bit or 4-bit. Based upon that, make a state transition, current state to next state, then write down the corresponding inputs based upon the flip-flop selected, D flip-flop or so which transition of Q to Qn Q bar Qn plus 1 will give the Q to Qn plus 1 will give corresponding inputs. Write down those inputs and for which input values it is 1, those minterms you do an K mapping and generate the hardware to be connected to the input pins, inputs of the flip-flops. So this covers the topic counters.
Circuit, and it just simply counts. If it is at 1, then the next time it will say 2, then 3, 4, and so on. Now the number from which it starts counting and also the number at which it ends the count depends upon your design. You can design your counter depending upon your need. For example, there may be a counter which counts from 0 to 10, and there may also be a counter which counts from 2 to 6. Similarly, there may be a counter which counts from 3 to 9. It all depends upon your design. So we know now what is counters, and we have to see it's working now. So let me rub this portion first, and we will analyze this circuit that you can see here, that is having the JK flip-flop, and as you remember, the flip-flop is used to store the memory, but instead of storing the memory, it can also be used for the frequency division that you will just know in a minute. So let me write this thing down about this circuit. It is flip-flop as divide by 2 circuit. Why I'm calling it divide by 2 circuit will be clear in a minute. There is a JK flip flop, you can see, and another JK flip flop is also, and the most important thing going in this 2 JK flip flop is the clock is not the same. You are giving a clock here. Let's say the frequency of this clock is FC, but as you can see here, the same clock is not given to the second flip flop, but we are giving the output of the first flip flop as the input to the clock. So this is the most important thing in your counters, and what we are going to use here as the value of JA, KA, JB, KB is 1. So let me connect JA with JB, similarly KA with KB, and we will give the input 1 to J and K. Now definitely toggling is there, and I have repeated thousands of times when we were studying the JK flip-flops that we are going to use the toggling in counters. We don't use the race around condition. It is a not usable form. That's why we converted it by using the master slave operation or by negative edge triggered flip flop. Here you can see this symbol represents that it is negative edge triggered. This bubble shows that it is negative, and this arrow shows that it is edge. Therefore, in total, it is a negative edge triggered flip flop. That's why we are overcoming the race around, and we are having the toggling action. So this toggling is very important for your counters. So let's see how this circuit works, and I will say the frequency here as FA and the frequency here as FB. Now I have made the clock here, and we have to analyze what's going on depending upon the change of the clock, and as it is a negative edge triggered flip flops, all the changes will occur on the falling edge when the clock is going from high to low. This is my clock. So all the changes will occur for this falling edge. Now, as I have already explained you, this clock is just given to the first flip-flop, whereas the output of this flip-flop is given as the clock to the next. So the changes that we will measure for this falling edge is only for the first flip-flop, and the output QA will be determined depending upon it. This QA then will be considered as the clock for our next flip-flop, and we will see how the frequency is changing. So let us try to find out QA. I am considering QA is 0 initially, so it is 0 till this falling edge, and as the toggling action is there, we are having the complement of the previous stored value. So the complement of 0 is definitely 1. So I'm having QA high for this interval. Again, we are having a change at this falling edge, and the 1 will become 0. Similarly, we can plot for the rest of the falling edges. Okay. Now the interesting thing will happen. This QA is now acting as the clock for our second flip-flop. So QB will not be considered depending upon this falling edges, but it will be considered depending upon this falling edges. This is acting as a clock for QB. So considering QB as low, so it will remain low till now. Then it goes high because of toggling, and again at this falling edge it will become low. So this is what we got from this configuration. Now you can check for the frequency. Here the time period, this is my time period, let's say TC, and if I check for the time period QA and I will call it TA. So you can clearly see TA is twice of TC. And as you know about the relation between the time period and frequency, which is f is equal to 1 by t, I can write t a as 1 by f a equals to 2 by f c, or I can write f a equals to f c by 2. So f a is equal to f c by 2. Now the frequency is half. That's why we call it as divide by 2 circuit. Now what happens to the frequency fc if we check here? So let's check for it. This is the time period TB, and TB is equal to twice of TA. You can see this is TA, and one more TA will fill up for TB. So 1 by FB is equal to twice of FA, or FB is equal to FA by 2, and writing it in terms of FC, I'm having FC by 4. So FB is equal to FC by 4. Frequency is now 1 by 4. So again it is divided by 2. So if we are having in total P number of flip-flops in which the value of J is 1 and K is 1, and it is negative as triggered, then in total we are going to divide the frequency by 2 to the power P. Okay, like in this case P was equal to 2, so 2 to the power 2 gives us 4, and frequency you can see is divided by 4. Similarly, if I am having 4 flip-flops, then 2 to the power 4 gives us 16. The frequency will be divided by 16. So this is the basic of counter. Till now it is not clear that how it is working as counter, but in a minute it will be clear to you that it is your counter. This is my counter and it is counting from this particular circuit is counting from 0 to 3. So let's see how it is counting from 0 to 3. I have given the clock pulses numbers 0. This is my 0th clock pulse. This is my first clock pulse, then second, then third, and then fourth. I have given them the number starting from 0 because we only have to count the clock pulses and the counter will work. So how we are going to know which clock pulse is elapsed? It will be determined by the value of Q and QB. So let us first write down the clock pulses and it is 0, 1, 2, 3. Then we are having our outputs QB, QA. So for this clock pulse, the 0th clock pulse, the QA is 0 and QB is also 0. So 0, 0. For the first clock pulse, the QA is having value 1, whereas QB is still 0. So 0, 1. For second clock pulse, QA is 0, whereas QB is 1. So 1, 0. And for this third, I'm having QA 1 and QB 1 as well. So 1, 1. Now you might be thinking why I'm not considering or calculating for the fourth pulse. I can show you for the fourth pulse QA is 0 as well as QB is 0. So again I am at this point and it will start counting 0, 1, 1, 0 and 1, 1. Then again it will become 0. So this is how this circuit is working as counter, and just by knowing the values of QB and QA you can know how many clock pulses is passed. 0, 0 is 0, 0, 1 is 1, 1, 0 is 2, and 1, 1 is 3. So by knowing this output, the output of my two flip-flops, I can know the clock pulses passed in this way the counter works. Similarly, you can make a counter that will count from 0 to 15. So how much flip-flop you require? You require 4 flip-flops. 2 to the power 4 gives you 16, and after 16 clock pulses, again the value of your output will become 0, and in that case we will be having 2 more outputs for the 2 more flip-flops, and we will check for that outputs. Let's say if they were QD, QC, QB, and QA, and it will start from 0 0 0 0 all the way to 1 1 1 1, and by knowing these outputs we can know how many clock pulses has been elapsed. I will not explain anything more about this counter because it may be confusing to you right now. It's very hard to understand these things itself. So I will leave you with this thing. Please revise it. Please understand it. If you have any problem, you may ask in the comment section, and from the next presentation we will study more about the counters, and at the end you will find that unite these synchronous counters, and we also took one example in which we designed the 2-bit synchronous up counter. In this presentation I will follow the same steps, the 5 steps that I explained to you, and we will design the 3-bit synchronous up counter. So the step number 1, the step number 1 is to determine the number of flip-flops to be used, and also we will decide the type of flip-flop. So what we will do, we will determine number of flip-flops, number of flip-flops, and we will decide type of flip-flop. So these 2 things we have to do in step number 1, and you already know the number of flip-flop is proportional to the bit of the counter, and here you can see we have to design 3-bit synchronous up counter. So the number of flip-flop, the number of flip-flop is equal to 3, because this output of the flip-flop. And as we have 3 flip-flops, we have 3 outputs, and thus the 3-bit of the counter. And I want to implement this 3-bit synchronous sub counter by using the T flip-flop. So we are done with this step number 1, and now we will move to the step number 2. And step number 2 says we have to make the excitation table for the decided flip-flop. And we have decided T flip-flop, so we have to make the excitation table for T flip-flop. So let's make it Qn, and Qn plus 1 are the 2 inputs, and the output is T. We have 2 variables, so 4 possible combinations: 0, 0, 0, 1, 1, 0, and 1, 1. Now we have to find out the value for T. When Qn is 0, Qn is my present state, and Qn plus 1 is my next state. When present state is 0 and also the next state is 0, it means the memory, the T is going to be 0. And when Qn is 0 and the next state is 1, it means we have toggling, and for toggling the value of T must be 1. And for the third case also we have toggling, and for the last case we have 0, because next state is same as the present state. So this is the excitation table for the T flip-flop, and step number 2 is now over, and now we will move to the step number 3. Step number 3 is, and in this step we have to do 2 things. The first thing is to find out the state diagram, and the second thing is to find out the circuit excitation table. So first we will find out the state diagram. 3-bit synchronous counter we have to design, and for 3-bit we know the number of state is 2 to the power 3, that is 8. So there are in total 8 states, and the maximum count, the maximum count is 8 minus 1, that is 7. So our count will start from 0, 0, 0, and it will end at 1, 1, 1. So let's make these 8 states first, then we will make the circuit excitation table. This is our first state: 0, 0, 0. This then we have 1 0 1 1 1 0, and finally we have 1 1 1. This is our maximum count, and you can see we have to make the up counter, so the counting will start from 0, then we will have 0 0 1 0 1 0, that is 2, then 3 4 5 6 7, and again we have 0. So this is the state diagram, and by using this state diagram we have to make the circuit excitation table. The first column of the circuit excitation table is the present state, and the present state is given by the three outputs, that is QC, QB, and QA. Then the next column will give us the next state, and S is the next state, and next state is QC plus, QB plus, QA plus, and then we have the flip-flop input TC, TB, and TA. So these are the three columns in our circuit excitation table, and we will find out the value of the flip-flop input by using the state diagram, and then we can implement it by using the K-map. When we are having the output as 0 0 0, you can see we are going to the next state, that is 0 0 1. So the next state is 0 0 1, and when we are on 0 0 1, the next state is 0 1 0, 0 1 0. It is very easy to find out the next state for the counter. If we are on 0 1 0, the next state is 0 1 1, and when the present state is 3, that is 0 1 1, the next state is 4 1 0 0. If the present state is 4, the next state is 5. If the present state is 5, the next state is 6. And if the present state is 6, the next state is 7, the maximum count. And if the present state is 7, the next state is 0. We are again back to 0. So this is what we have derived from this state diagram, and now we will find out the value for TC, TB and TA. First I will find out the value for TC, and it is nothing but the input to our T flip flop, and for that we have to compare QC and QC plus that we can do from this table that we derived earlier. This is the excitation table. This is the present state. This one is the next state, and by using it, we can have the value for T. So let's do it. For the first case, QC is 0 and also QC plus. So present state and the next state are same. It means the memory, and in T flip flop we have memory when the TC is equal to 0. Similarly, you can see for the second case again we have the same state, and for the third case again the same state. For the fourth case there is toggling. The present state is 0 but the next state is 1, and for toggling TC must be 1, and this case is having the present state 1 and next state as 1. So again we have the memory, and for this case also we have TC 0, and the second last case TC is 0, and the last case we have toggling. In the same way I will complete TB 0 0. So 0 0 1 toggling. So TB is 1 1 1, same state. So TB is 0 1 0 toggling. So TB is 1 0 0, again same state. So TB is 0 0 1 toggling. TB 1 1 1, again same state. So 0 1 0 toggling, and for TA you can see we have always toggling 0 1 1 0 0 1 1 0 0 1 1 0 0 1 and 1 0. So I will write TA as 1 for all the 8 cases. Okay, now we have TC, TB and TA. We can use a 8 cell K map to find out the minimized value for the 3 inputs. So I will just paste a 8 cell K map, and definitely we require 3 such maps. So I will paste 2 more, and the inputs are Q, C, Q, B, Q, A, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, and this is for TC. TC is 0, 0, 0, 1 for the first four cases. So 0, 0, 0, 1, and for the last four cases it is 0, 0, 0, 1, 0, 0, 0, 1. We have a pair of 1 here, and thus TC is equal to QB, QA. Now we will solve for TB. The inputs are QC, QB, QA, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. It is 0, 1, 0, 1 initially. So 0, 1, 0, 1. Then we have 0, 1, 0, 1 again. So 0, 1, 0, 1. We have group of 4 ones. Thus TB is equal to, you can see QC is changing from 0 to 1, and QB is also changing from 0 to 1. Only Q is not changing, and it is 1. So I will write TB equal to QA, and now we will solve our last K map, and this is for TA. The inputs are QC, QB, QA, 0, 0, 0, 1, 1, 1, 1, 0, and 0, 1. It is 1 for all the cases, so there is no problem. In this map we have the group of 8 ones, and TA is equal to 1. Now we will implement it, and this is the last step, the implementation. We have 3 flip-flops, 3 T flip-flops. I will make these 3 T flip-flops. This is my first flip-flop. This one is second flip-flop, and this one is third flip-flop. Now we will implement the logic that we have evaluated from the K map. This is the A flip-flop. This is B flip-flop, and this one is C flip-flop. TA is the input for the A flip-flop, QA is the output of the A flip-flop. Similarly, TB, QB, TC, QC. And as we are designing the synchronous counters, definitely the clock is simultaneous. So we have to give a common clock to all these three flip-flops, and this is the way to do it. This is clock, and now we have to implement the logic. First I will implement TA. TA is 1, so I will simply give the logic 1 to TA, and TB you can see is equal to QA. So I will make TB equal to QA, and I will simply join them, and TC is equal to QB QA, and we have to use the AND gate for this. So I will use an AND gate here, and the input to this AND gate is QB, and the second input is QA. So I will take QA from here and give it to this 2 input AND gate. The output of this AND gate is then given to TC, and you already know the output for the clock is QA, so we have to take QA, and QB is the second bit. This is LSB, and QC is our MSB. So QA, QB, QC. Output of the counter, and they will start from 0 0 0, and they will end at 1 1 1. In this way you have to design a 3-bit synchronous counter. I hope you got these things, and if you have any problem relating to this presentation, any doubt, you can ask in the comment section.